introduce some probability here as we move into the second unit. We want to be able to show we can use the terminology of probability properly and then calculate some of the basic probabilities using multiplication, addition, and the complement properties. So let's get into it. Let's say we'd like to flip a coin. Now, instead of having to flip a coin by hand, what we can do is we can actually simulate this. We can simulate it using the calculator. So the first thing we want to do, let's talk about what are we trying to do. We can define the events. So when we flip a coin, it's either going to be heads or tails. Now, if we're going to use a calculator, we think about it, a coin should be a 50-50 split, right? If we're flipping an imaginary, and I should say fair coin, it's 50-50. So what we can do is, using our random number generator in the calculator, we can use digits 0 to 9 if we want. The idea here, we need to split it 50-50, so we could do heads are the first 5 numbers, tails are the last 5. Or you could do evens, heads, odds, tails. Probably one that makes a little bit more sense is let's just use 2 digits, random digits 1 and 2. Then we come back, how many trials we'd like to do, and then we execute the simulation. So real quick, now that we're here at the calculator, you can see, so you hit the math button, and we scroll over to the probability function, down to random integer. Hit enter. And then what we're going to do, we need to tell the calculator between what 2 numbers to pick. So we do 1 and 2. Now, let's say we wanted to flip the coin 5 times. We'll put that next number in there. So now all of a sudden, when we flip our imaginary coin, we got tails, tails, heads, heads, heads. If we hit enter again, we can see now we got heads, tails, tails, heads, heads. If we keep kind of doing this, all of a sudden we might run into something that looks kind of funky. Here's 4 tails in a row, which you don't really expect a fair coin to do. So how does that probability work? Well, what you just saw in the calculator were a bunch of experimental, or a better term for it, empirical probabilities. And an empirical probability is from observing, from doing something. That's what we just did. We just did some simulations, right? In that last example, if you think back, the probability of heads, our empirical probability, 1 out of 5. Now that seems odd, but the thing is, chance behavior is very random in the short run. In the short run, we could get these crazy runs, like only 1 out of 5 heads. But the law of large numbers says that if I keep doing something over and over again, so the long run relative frequency, so in other words, the long run probability, that's what this term right here, relative frequency, is saying. The long-term probability should settle down to the true probability over time. So if I just kept doing more and more flips of the coin, if I flip the coin 5,000 times, it'll be a lot closer to 50-50. So this true probability, another name for it, is theoretical. And that's what's going to happen. A mathematical model, this random phenomenon, it should be 1/2 for a coin, obviously, if it's fair. And the law of large numbers says as we keep doing it more and more, our empirical, what we see on the calculator, what we actually do by hand, should get really, really close to the theoretical, if not right at it. Some of the terminology we want to talk about: trial, that's any kind of random event. Outcome would be the value of a random event. Sample space, the set of all possible outcomes. We did an example in class where Uncle Bilbo was flipping a coin, and we had him flip the coin 4 times. One of the outcomes we were interested in, what's the probability he gets 2 heads and 2 tails? Other outcomes we were interested in, we're also interested in 4 heads or 4 tails. That was another outcome. At least 1 tails. That was another outcome. To get the ball rolling, if we talk about the sample space, what are the 4 possible outcomes if we flip a coin 4 times? Right? We could get heads, 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 heads. We could get heads, 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 tails, so on and so forth. So altogether, this is the entire sample space for Uncle Bilbo. Now all of a sudden we see now we see there's 16 different outcomes that could happen. Here, let's say we roll a fair die 2 times, right? We got our 2 dice. All right, we're going to roll them twice. Or roll 2 of them. Right? These are all the possible events. You can roll a 2, 3, 4, 5, all the way up to 12. Well, if I think about the sample space here, each of these outcomes is not as equally likely. There are 36 total outcomes, But as we can see, it's a lot more likely that we roll a 7 than it is we roll a 2. If we go back to our Uncle Bilbo example, the trick here, these actually aren't all as likely. This is not as likely as this, and that's because if you recall, the probability of flipping a head is 7. So a lot of these probabilities are going to shift a little bit. It's not quite as straightforward as the dice example, because even though there are 16 outcomes, this is not out of 16, because again, it's not a fair coin. Should this be a fair coin? It absolutely would work that way. Another quick example that's in your note packet. Let's say a family's going to have 3 kids, and you like to see, well, how many boys could they have? Well, there are 3 possible outcomes. They could have 0 boys, 1 boy, 2 boys, or 3 boys. Are they all as likely? The answer to that is no. Probably the best way to think about that then is come up with a sample space. So how do they have 0 boys? They have all girls. How could they have 1 boy? Well, there's 3 ways to have 1 boy. They could have the boy first, second, or third, and all of those are unique families. 2 boys, they could have 2 boys first, a girl in the middle, or 2 boys last. And then how many ways are there to get 3 boys? 1 way. Now, in this particular case, the probability of having a boy is the same as the probability of having a girl, and it's about 50-50. So here, all of a sudden, we're going to see that we can just say there's 1 way to have 3 girls, so 1 out of 8. There are 3 ways, 3 out of 8, to have 1 boy. So this time, again, the probability of 1 boy and 0 boys, they're not equally likely, but each individual outcome is the exact same since it's a 50-50 shot at a boy or girl. Some of the properties of probability. Probability always must be between 0 and 1. The entire sample space will always add up to 1. If we go back to the example you just saw, if we add these up, 1/8 plus 3/8 plus 1/8 plus 3/8 equals 1. Um, go back to this. If I add all of these fractions up, they add up to be 1. This is what's called the complement. Right? Both of these mean the exact same thing. Some texts still use a superscript C. Some will use the bar over the top. I typically go with the bar over the top. But the idea, the probability of an event occurring is 1 minus the probability it does not occur. And we're going to use that in a minute. The addition, the probability of A or B happening would be A plus B. Now that's if they're disjoint. If they are not disjoint, which means that there's some kind of overlap, you have to do the probability of A plus the probability of B. And then you'd have to subtract that overlap. So this is A and that's B. We just want to make sure we don't double count that middle section. So this right here would be if they are not disjoint. What I think is I put in the note packet if they are not mutually exclusive. And then the other rule, the multiplication rule, the events of A and B happening would be probability of A times B. That again is only true if these things are independent. Now, independent and disjoint, 2 different concepts, but we'll get into that later. Let's say we're going to do an example of M&M. So 20% of the bag is yellow, 20% of the bag is red, 20% red, 10% is orange, 10% is blue, 10% is green. Right off the bat, they ask us what's the probability we get 3 browns. Well, brown's not in the original thing, but if we add them up, I believe these add up to 70%. Using a basic probability principle, the entire sample space has to go to 1 or 100%. The probability we get brown then would be 0.3. So if we get 3 browns in a row, 0.3 times 0.3 times 0.3, which puts us at 0.027. The third one is the only red. That means the first one is not red. Here we're going to use that complement rule right off the bat. And if we want not red, well, 20% are red, which means 80% are not. We go right there, and that'll be 0.128. At least one green, right? This one we're going to come back and talk about in just a minute. 2 yellow. Now the trick here is we could get yellow, yellow, not yellow, or we could get yellow, not yellow, yellow, or we could get something that's not yellow followed by 2 yellow. The thing of it is each one of these is the same probability. We're just going to add them all together. So the probability of yellow was 0.2, 0.2, that's 0.2 times 0.8 times 0.2, 0.8, 0.2, 0.2. The quicker way to do this is think about how many ways are there to get 2 yellows. Well, there are 3 ways. So we could just do 3 times 0.2, 0.2 times 0.8. But as you see with my work, it's sitting right there underneath. It's pretty straightforward where that's coming from. Why we have that 3 there, we have the same thing 3 times. So that probability, 0.096. Now that's at least one. A little bit tricky. The hard way to think about this is at least one means it could be 1 green and 2 not, 2 green and 1 that's not, or 3 green. Well, there are 3 ways to get 1 green. Right? This would be green, green, not green. There's 3 ways to do that. Just like there are 3 ways to get 1 yellow, there are 3 ways to get 2 greens. Just like there were 3 ways to get 2 yellows. And then there's only 1 way to get 3 greens. Now, in terms of this being the hard way, this actually isn't that bad with only 3 M&Ms. But there's a much easier way. If we think about it, the opposite of at least 1 is nothing. What we want to do is if we can think about this complement rule, right? The probability of something happening is 1 minus the probability it doesn't. Well, the opposite of at least 1 is no green. So if we can do 1 minus no green, that puts us in a great spot. So one of the big tricks for us, probability of at least 1 equals the probability, or 1 minus the probability of none. It's a huge principle that we want to think about moving forward in this class. Anytime you see at least 1, start thinking about doing something the opposite. I'll give you another example. We did this one in class with Uncle Bilbo's trick coin. At least 1 tails. So we'll go right back to the at least 1. Again, here's how it could work. At least 1 tail, that means it could be 1. Here's all the examples of 2 tails. Here's all the examples of 3 tails, and then there's 4 tails. Well, the thing of it is we've got a lot of ways to get at least 1. Now, there's only one example up here, heads, 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 that's not got a tails. By our basic probability principles, this whole thing should sum up to be 1. If I took all 16 probabilities and added them up, they should be 1. The idea maybe behind seeing that this complement rule is a really, really solid rule to use. We either have to figure out all 15 of these and add them up, or knowing that they should all add up to 1, if we can figure out the probability of all heads and subtract it from 1, that would give me what's left in the circle, right? So the probability of at least 1 tails, the opposite of at least 1 would be probability of no tails. So maybe you can see it in the picture. Really, if I know what this one thing is up here, all I have to do is pull that back from 1 and I get what's left over, which is everything in this circle, which happens to be at least 1 tails. So 1 minus the probability we get 3 heads in a row on Uncle Bilbo's, or 4 heads in a row, excuse me. 1 minus 0.7 times 0.7 times 0.7 times 0.7. That is 0.7599, 0.76 if you round earlier.